Okay, so I think we're ready to introduce junior global Poisson. So Nastya, would you like to kick it off?
Oh well, we had the last minute change of schedule. I thought you were going to announce that. No. Well, in case someone still haven't noticed, we had a last minute change of schedule, and the stand of Charlotte, we're having Leonid Ryvkin as our first speaker. Thanks a lot, Leonid, for helping us, for covering this spot. And his talk will be about multisymplectic comoment geometry.
So, before we begin, actually, so I want to say a little bit about the format. So the format is every speaker will get clean 25 minutes. All the participants will be muted. You won't be able to unmute yourself, and we encourage you to relegate questions until the parallel session. You can ask questions in chat, and then we'll try to collect them and give them to the speaker. And for the speakers, so you'll have 25 minutes clean, and then so after 20 minutes after the start of your talk, I'll unmute myself and give you a 5-minute warning. And then when 25 minutes hit, well, we'll see. Maybe you'll get kicked out. we'll decide on exactly the procedure. Okay, so I think there are no more questions. Let me just do the very last minute check. Okay. 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 So now I think so. Now Leonid, you're the only one who has the microphone unmuted. So Nastya, would you like to introduce Leonid one more time just before we go?
Yeah, sure. So again, as I said, we're having Leonid Ryvkin as our first speaker, and he will talk. And he will talk about multisymplectic comomentum geometry. Leonid?
Okay, so hi everyone. And first of all, thanks a lot to Nikita and Anastasia for organizing this event. I'm full of anticipation, and it's really well organized. And I love the fact that there are social activities, but more about that later. I'll try to tell you a little bit today about multisymplectic comomentum geometry. Given that multisymplectic is not completely common knowledge, I'll start by explaining multisymplectic. Then I'll give a brief reminder of comomentum in the symplectic case, and then finally I'll combine those terms. Okay, so but before I start, just a comment on the naming of this event that Matteo has just made in the coffee break. So according to Nikita, this event involves some kind of audience, but there is not more than one talk, but you have to pay for it. So we are on a workshop. You can read the remainder of the comic later. It is in the chat. Okay. What I'll talk about today is joint work, first of all, from a few years ago with my thesis supervisor, Tilman Wurzbacher, and 2 more recent articles with Antonio Mitti and Leili Mamadova, who are PhD students and soon to be postdocs at Leuven. I should note some of the central articles in the field, which is this article by Martin Calisi, Alfregier, Chris Rogers, and Marco Zambon, where the notion of homotopy moment map or multisymplectic comoment was introduced. I should say that the paper of Tilman and me came out at the same time and had the same content as, or essentially the same content as this paper, but we found that independently. And the notion of weak moment maps is due to Jonathan Herman, based on earlier work of Madsen and Swan. So let's get started with the mathematics. The definition of a multisymplectic manifold is a manifold with a differential form which satisfies two properties. First of all, it's closed, so the de Rham differential of the form is 0, and non-degenerate. A closedness is the same as in the symplectic case, while non-degeneracy is a slightly weaker statement. So normally, in the symplectic case, we require the map between tangent bundle and cotangent bundle to be 1-to-1, but the tangent bundle and the, let's say, a multi-cotangent bundle have different dimensions in general, so we cannot require that. So non-degenerate in the multisymplectic case means that this map is injective. The form somehow sees all directions, but yeah, not every higher degree form can be associated by contraction. So the first example, of course, is symplectic. This is also the reason why we say that something is k-plectic. If it is a k+1 form, we want k equal to 1 to be symplectic. And also in the k equals to 1 case, we have a Lie algebra of observables. And in the k equal to 2 case, we have a Lie2 algebra, which will become more clear later. So k equals to 1, symplectic is the first example. And k equals to dimension of the manifold -1 is the last example. It's the case of a volume form. Those two are actually the only two cases where the stronger non-degeneracy, the bijectiveness of this operator, is possible. So all cases in between, we only have injectivity. Just to name one of these cases, kind of k equals to 2, the next case. If we take a semi-simple Lie group and with its killing form, then we have a canonical 3 form on its Lie algebra. We can extend this free form B invariantly and get a 3 form on the group. And as it is B invariant, it is automatically closed. And the semi-simplicity implies non-degeneracy. So semi-simple Lie groups are 2-plectic. They carry a multisymplectic 3 form. I will already do a little advertisement. There are many, many more examples. For instance, the same way that T star Q is a symplectic manifold, lambda K T star Q is a multisymplectic manifold, which is motivated by jet bundles for classical field theories. Further examples include G2 structures, strictly nearly Kähler manifolds, and also some unimodular Poisson structures. I'll say more about this in the parallel session. Now, a quick reminder about symplectic moment maps. We look at a symplectic manifold and a Lie group acting, let's say, from the right, preserving the symplectic form. Then we say that a moment map is a map from M from M to the dual of the Lie algebra, such that if we compose by the contraction with any element of the Lie algebra, then we get the function whose Hamiltonian vector field is the infinitesimal generator of the action. So somehow for infinitesimal generators of the action, we get a choice of Hamiltonian function from which they come. And we require this map not only to be linear, but also to be equivariant. That is, the action on M turns to the co-adjoint action on the Lie algebra. I'll rewrite it in the dual form. So in the case when G is connected, the infinitesimal information suffices. then we can look at the map from the Lie algebra to the smooth functions that, first of all, lifts the infinitesimal action. So we have the infinitesimal action here. And we have the association of a function having a Hamiltonian vector field here. And we want this diagram to commute. This is the translation of the first property. And the second property, the equivariance, translates into this map not being a linear map, but also a homomorphism of Lie algebras. And the Lie algebra structure here is probably your favorite Lie algebra structure. It's the Poisson bracket of functions, sometimes called observables. In lingo coming from classical mechanics. And we want to construct something analogous for multisymplectic manifolds. Why do we want to do that? Because moment maps are very useful. They have applications to conservation laws or conserved quantities. They are necessary for reduction schemes and ultimately also for pre-quantization or quantization, which in the context of field theory are all quite interesting goals. So what we need to generalize this to the multisymplectic case is we need to understand what observables should be for multisymplectic manifolds. What's the analog of the Lie algebra structure on the functions? And here is the construction which we'll use for it. So we use the standard equation that that usually is defined to associate a Hamiltonian vector field to a function in symplectic geometry, and we just translate it one-to-one to the multisymplectic case. But now, if this is a k+1 form, this has to be a k-1 form. And we notice quite fast that because of non-degeneracy just meaning injectiveness and not bijectiveness, this will not be solvable. This equation cannot be solved for all forms. But this is not a big problem. We just say that we look at a subspace of forms where this equation has a solution. This is a subspace of k-1 forms. And we can, similar to the symplectic case, just define a bracket on it. So for two forms, we just contract their Hamiltonian vector fields into omega and get a new k-1 form. And indeed, this form will be Hamiltonian again by construction. Unfortunately, this bracket we just defined is not a Lie algebra bracket. So the Jacobi identity is not satisfied. If we take brackets of 3 elements and permute cyclically, we don't get 0, but we get d of something. And now if you are familiar with homotopic algebraic structures, you already know where we are going. And also, if you read the title of the slide, you know where we are going. This forms a Lie algebra up to homotopy, or something which is called Lie infinity algebra. We add higher degree or lower, depending on your perspective, degree to the Hamiltonian forms. We just extend it by the de Rham complex in all lower degrees, right up until functions. And we say that this error to the Jacobi identity, it's not a bug, it's a feature. It gives us more information. So we define the thing which stands here as a bracket taking 3 elements. And this bracket will again satisfy an identity up to d of something. And now we call this something a bracket that takes 4 elements and so on. And what we get in total is the following formula. So the unary bracket or differential is just the de Rham differential. And all the higher brackets are basically defined by, we are taking a bunch of k-1 forms. We get their Hamiltonian vector fields, and we put them into omega with an appropriate sign that you shouldn't worry about. And this construction is due to Chris Rogers, who found that this construction yields an L-infinity algebra. So we take the vector spaces Li, which are essentially a part of the de Rham complex. We take the first bracket being the differential and the higher brackets that I have just defined, which, just as a note, are only non-trivial on the Hamiltonian forms, so on the lowest degree part. More about that in the parallel talk. And this construction yields an L-infinity algebra, so something that satisfies this slightly frightening formula, which somehow is in the end just the generalized Jacobi identity or identities, where we have a bracket of some elements, and the result of this is applied to a bracket of further elements. So we do have somehow the binary brackets, for example, with all cyclic permutations. Those are, you could say all permutations are just the unshuffles, as you like. It does not matter for the instance. But you also could have, for example, D, so the unary bracket of the bracket of 3 elements. Or you could have the bracket taking 3 elements applied to the unary bracket. This would be the terms of the standard Jacobi identity. And due to the quite simple structure of this concrete L-infinity algebra, those terms will be 0. And we'll have Jacobi up to D of something. So Chris Rogers found this L-infinity algebra for multisymplectic manifolds, and also an L-infinity morphism into the vector fields, which is surjective onto the Hamiltonian vector fields. Now, this gives us the possibility to simply define homotopy comoments, as done by Frege, Rogers, and Zambon in 2013, as an L-infinity morphism to this L-infinity algebra that lifts the infinitesimal action. So this is the algebra we just defined, which is part of the de Rham complex. And we say that a comoment is an L-infinity morphism. And even if you don't know what an L-infinity morphism is, you probably will believe me that it's a category, so there is a notion of morphism in there. In the parallel talk, I'll say more details about it. Luckily, as the L-infinity algebra is quite simple, we do have explicit formulas which one can read. So an L-infinity morphism from a Lie algebra to this L-infinity M omega algebra is given by a bunch of maps, not only one map, starting with F1, going from G to L0, that, as a reminder, were the Hamiltonian k-1 forms. And we want this component to project correctly onto the vector fields. This is the first property, which just says this is actually a lift. And the second property, which encodes the right notion of equivariance in this context, says that this is actually an L-infinity morphism. It's not really well visible here, but what you have is the binary bracket to the Lie algebra, and then applying one of the components of the comoment map. Then you have applying to the next higher component of the moment map, and then using the differential of the L-infinity algebra, and a term which involves omega, which more or less is the multi-bracket of the L-infinity algebra. Again, if you are not familiar with L-infinity algebras, don't care about it too much, because our first theorems will basically say you don't have to worry about it. So the first theorem tells us when a comoment exists. Using the above description, we can derive obstruction classes, which lie in the tensor product of Chevalier-Allenberg or Lie algebra cohomology and the RAM cohomology of the manifold. And well, those classes are zero if and only if an L-infinity morphism exists, if a homotopy comoment exists. Just a quick reminder, this is, in the symplectic case, this reduces to the standard theorem stating that these two classes obstruct the existence of a symplectic equivariant comoment map. Now to what we did with Antonio Mitti was that we translated this obstruction into geometry. So if you don't like double complexes, if you don't like L-infinity algebras, you can just look at the whole thing in cohomology. In this talk, I'll restrict to the case where the group is compact. We have a statement for non-compact groups too, but the statement is somehow more neat to explain in a brief time for compact groups. So we have an action which preserves the multisymplectic form, and a comoment exists if and only if this one cohomology class in the cohomology of M times G is zero. If you like groupoids, you might want to look at this class as coming from this groupoid. And it's actually quite useful because from this perspective, it becomes very clear that if you have, oh, now the groupoid disappeared, sorry. If you have an equivariant cohomology class extending omega, then you also have a comoment because you have an exact sequence, not an exact sequence, sorry, a sequence from HGM to HM to HM times G. A particular case of it is the case of an invariant potential for the multisymplectic form. I put in the invariant just because we need invariance in the non-compact case. So I want the statement to be true non-compactly too. So in the case the multisymplectic form has an invariant potential, then you also have a comoment. Those results have been already in the literature before, but using this criterion, it's they're quite simple to derive. And you also can derive other results, which were first found by Shabazi and Zambon in 2016 about existence of comoments for product manifolds. Now, the second theorem with Antonio concerns spheres. We look at an n sphere with the standard volume form and a compact group acting effectively on it.
Leonid, that's a 5-minute warning. Sorry.
Okay, thank you. And we say that this action admits a homotopy comoment if and only if n is even or the action is not transitive, which when we found it was a little bit surprising because we thought that all spheres should behave similarly in this context. But as it turns out, even for the standard SO n+1 action on Sn, if the sphere is even, we have a comoment. So S2, the symplectic sphere, has a comoment, S4 has one, and so on. And S2n-1 does not. On the other hand, for non-transitive actions, for example, SON acting on Sn, so we have, for example, fixed points, we always have a comoment. So once per talk, one should make a proof, even if it's very shortly. Basically, the cohomological obstruction reduces to only one group in this context, which is pulled back from the volume form of the sphere by means of the orbit map. And in case of an intransitive action, we can factor this map through an orbit. And if this orbit, there always will be, in an intransitive case, an orbit which is of lower dimension, and then this here the obstruction will be 0, so it will be 0 here also. And in the transitive case, there is a classification of effective group actions, and we check case by case what happens to the cohomological obstruction. So in the case of spheres, we don't always have a comoment map, even though spheres with SON actions are a very, very symmetric object. It would be nice to have some notion of moment even for them. And this notion has been introduced by Jonathan Herman. It's called weak comoment map. And it basically is a comoment map, but only restricted to cycles in Lie algebra homology. And otherwise, the identity satisfied are the same. I'll talk more about that in the parallel talk. And this definition, which is only defined on a subspace, this notion which only defined on a subspace has the advantage that if certain de Rham cohomology groups are 0, then it automatically exists. We only need exactness in one complex. Consequently, for spheres, they always do. So we have a notion of moment map for all spheres, even the odd ones. And finally, with the work with Laley, which I'll go into more detail about in the parallel session, is that the only difference between a homotopy comoment and a weak comoment is the last obstruction class. So the theorem is a weak comoment exists only if and only if Ci are 0 for I from 1 to k, whereas in the comoment case, we had 1 from k to k plus 1. There is only one additional obstruction class. So thanks a lot for your attention. If I have half a minute, I'll just say that in the parallel talk, I'll make comments on the details about the L-infinity algebras involved that I just skipped over just now, and maybe talk a little bit about conserved quantities. Okay, thank you.
Thank you very much, Leonid. So we can applaud with stickers, and you can imagine the sound of applause. Oh, look how many. Very good. Thank you very much.
I can see it while I share my screen. I may unshare it, right?
Yes, you can now unshare it.